Hello and welcome to a new video. My name is Herwig and today we discuss property versus temperature data of polymeric materials. Okay, let us get started. First, a word on multi-point data. So why are they so interesting and also important at the same time? So multi-point data allow for better decision making in the polymer material selection process for your part or applications. So when you think of material selection itself, it has to do a lot with thinking in relationships, mainly time dependency and also temperature dependency behaviors, which is really important with polymers. And such temperature dependency behaviors, for example, can be better shown graphically and not over a single point value in the table. So classic example of single point data is the technical data sheet of a material. Let's take, for example, the modulus value at 23 degrees C. However, this can lead to a misjudgment and can negatively impact your material selection, because we most probably need the modulus at the temperature or at the application temperature, which is, for example, 150 degrees C. And there the material, depending if it is amorphous or semi-crystalline, can behave completely differently. So for this discussion today, I've selected three technical properties which are interesting and for material selection. So we have the thermal conductivity as a function of the temperature. We have the coefficient of linear thermal expansion versus the temperature, and the specific heat capacity versus the temperature. Okay, let's start with the thermal conductivity versus the temperature. What you can see here is on the y-axis the thermal conductivity in watt per meter Kelvin, and on the x-axis the temperature. We start at minus 150 up to 200 degrees C, and in this chart we see mainly the amorphous polymers. So we have here PMMA, polystyrene, PVC and polycarbonate, and there we see already first also those are unreinforced and unfilled, so it's really just a natural polymer. And there we see already that the thermal conductivity, I mean, as we all know, it's they're quite low with polymers, so it's the reason we use them also as for insulating reasons. And what we also see, it's a non-linear behavior. So at minus 150 we start, for example, with PMMA around 0.15 watt per meter Kelvin, and then we have an increase towards room temperature, and then it levels towards higher temperature. So it's not so much change, it's more the change in the lower temperature area. And this you can also good see with polycarbonate. It starts in a similar level at minus 150 as PMMA, and then it much stronger increases towards room temperature, and at higher temperature the level is at almost 0.25 watt per meter Kelvin. And here we have the semi-crystalline behavior of the thermal conductivity versus the temperature. So I've selected polyolefins, so polyethylene, polypropylene. We have some polyamides and also some fluopolymers. And for example, when we take PTFE, polytetrafluoroethylene, it has over the whole temperature range, so from minus 150 up to 150, the same thermal conductivity. And however, when you take, for example, high density polyethylene, so it's this orange cross here, we start at low temperature with high thermal conductivity and then decrease at higher temperature. So it's also again a different behavior. And long chain polyamides, for example, the PA610, they have also almost constant over the temperature. So it's always good to have a look how this behaves. Then coefficient of thermal expansion, so the CLTE versus the temperature. And so here I have both now amorphous and semi-crystalline in one chart. Again, the CLTE, so the property on the y-axis, and then the temperature on the x-axis. This time it's logarithmic view, and there we can also see, because the CLTE is important when you combine it, when you have two component molding or over molding of a metal, or when you do metal replacement. So you need to know how the material expands, and it's always 10 the power minus 6, so per Kelvin. So it's how many millions per Kelvin the part is expanding. And here we also see the different behavior. I know it's lots of curves, but it again shows important behaviors from minus 150 and then at 250. So when we take the PTFE, for example, it really expands then from minus to the positive temperature. And then we have the heat capacity in joule per kilogram Kelvin. Again, y-axis, and on the x the temperature, and there also mixed, unreinforced, unfilled, amorphous and semi-crystalline polymers, and to show how the heat capacity of the different polymers is changing over the temperature range. This is important for processing. You need to know how much the material can take up on heat for the melting in your extrusion or injection molding process, for example. And I will link you all these charts and also more information. So I made also a blog posts on findoutaboutplastic.com with all those property versus temperature charts. So I will link that in the description below. Okay, so that was it for today. I would like to thank you for watching. Until next time, bye.